To start with our first technical session, we have Mr. S. Gopakumar and Mr. Krish Theobald with us. Our first speaker, Mr. S. Gopakumar, is an electrical engineer, managing director of Cape Electric. He has more than 28 years of experience in electrical safety. Mr. Krish Theobald is also the speaker of this session. He has a great expertise in UK's national wiring regulations. He is the technical director at Protego Plus Electrotech Private Limited. He is a currently member of the Institute of Engineering and Technology, UK. Mr. Krish has appeared in several podcasts and shows in the UK, including Hit the Lights podcast and FX Live. He is passionate about promoting a culture of electrical safety in India. Electrical safety is not an option, it is the necessity of human life. I request the speaker, Mr. S. Gopakumar and Mr. Krish Theobald, to enlighten us on the topic, National Electrical Code of India 2023, Contents and Concepts of Electrical Safety in Consumer Premises. Now we will learn about the precautions to take against the electrical shocks and thermal effects, overcurrent and short circuit. With warm greetings, I welcome you both on the dais. Thank you.
Thank you very much. Thank you very much, gentlemen. So now we are going to start the technical session. The first technical session is about fundamentals of electrical safety as per the National Electrical Code. When we talk about fundamentals of safety, there are few fundamental safety requirements which no one can violate. Fundamental requirements no one can violate. There are 4 fundamental requirements. The first one is protection against electric shock. Don't look at the screen because the screen I am just, it is setting. Before that I thought of speaking. The first one is protection from electric shock. The second one is protection from thermal effect, which is nothing but the heat effect, fire, arcing, so on. The third one is protection from overcurrent, and the fourth one is protection from over voltage. These are the 4 fundamental requirements. Now, if we look at the protection from over voltage, example, there are different kind of over voltages applicable in the in an electrical installation, starting with over voltage due to, for example, high voltage it will work. Is it working? Yeah, thank you. So over voltage due to various reasons are there, due to lightning, for example, then due to fault on the high voltage system, fault on the low voltage system, loss of neutral. So like that, so many fundamental requirements are there. First we are going to talk about the fundamental electrical safety requirements. To start the fundamental, first we should understand that the first few slides, what I am going to show is about little bit introduction, then we go to the mandatory requirement, which as Mr. Umashankar told, the CEA regulation has made NEC as mandatory, so don't try to violate, because this has become now mandatory. Mandatory, the word mandatory, all of you know very well. The fundamental concept with respect to electrical system, there are 2 types of electrical system for the consumer premise. One is the earthed system, next one is the unearthed system. Earthed system is for places where the continuity of supply is not very important. The safety measure to be implemented is called as protective equipotential bonding and automatic disconnection of supply. I go into it in detail later. The second safety measure or the second concept is called as continuity of supply, or places where you cannot trip your protective device. For example, hospitals, telecommunication centers, data center for the rack. Those places, the second concept has to be adopted. The second concept is called as unearthed system. Means all the current carrying conductors are either insulated or one of the conductor is earthed through a high impedance. Here the idea is, in your installation, even if there is a fault, you don't need to trip the supply. Continuity of supply for the first fault must be ensured. These 2 are the technical requirements. Today we will talk more about the first one, which is the earthed supply, which we generally use in our electrical installation. Where you can see this information is IS 3043, part clause 5. You can find more details about this particular requirement. If you look at NEC, part 1, section 18 or IS 3043, you can find this kind of a table which talks about the maximum allowed disconnection time. This is very much important with respect to the first fundamental electrical safety requirement, which is protection from electric shock. On the left side, what you are seeing is the prospective touch voltage, means the voltage which is applied or the voltage which is available at the body of an equipment, touch voltage. And condition number 1 and 2, condition number 1 is the dry condition, means the environment is dry, the floor is dry, the person's body is dry. Under that condition, I have highlighted 220, means the fault voltage is 220. Within 170 millisecond, the protective device should trip. In case of wet condition, within 35 millisecond, the protective device should trip. Now, in order to check this, various methods have been implemented or introduced in the standards. Now, you know there is a meter available. You connect the meter, you check whether the impedance is correct in the circuit and your protective device is able to trip. All these things are there. So, the first measure about shock, let us start. I am sure all of you know this particular graph, the amount of current through the body and the duration of that current flow, which is going to create probably a shock or a tinkling effect or whatever. According to me, this graph is not very much required for an electrical engineer. This is for the researchers. Let them do research and find out whether the current is little bit more or less. You don't need to look into this particular chart always. What you should look is this chart, this table, or this the graph. This is, you can find this graph in almost all IEC basic protective standards, the same graph. This graph explains the prospective touch voltage. Here you can see the touch voltage and the disconnection time, touch voltage and disconnection time. If the touch voltage is going beyond this graph, a person get electrocuted and he may die. So, any electrical installation, be it low voltage, high voltage, extra high voltage, AC, DC, whatever, this is actually applicable for AC. There is a maximum allowed touch voltage for AC. This is the graph. I have put the timing and the maximum allowed voltage on the table. For example, generally we say a voltage of within 10 seconds the voltage has to be reduced to less than 65 volt. It doesn't mean that before 10 seconds you can go to any high level. It is not like that. So, this is the first electrical safety measure. Any electrical installation, the shock voltage must be reduced to a level lesser than this. Now, to achieve that, we have safety measures called as basic and fault protective measures. Basic protection, earlier we used to call this as protection against direct contact, and now we call as basic protection. In the new standards, upcoming standards, more than direct contact you will see basic protection, and for indirect contact the new name which is followed internationally is fault protection. Earlier we called direct protection and indirect protection, whereas our protection against direct contact and indirect contact, now we call as basic protection and fault protection. Now, with respect to basic protection, there are several basic protective measures such as insulation of live parts, barriers or enclosures, obstacles, placing out of reach. These are the 4 recognized basic protective measures. Now, basic protection is not always enough. In a good installation where you have basic protective measures, due to a fault, a person may get electrocuted. In order to avoid fault protection, the fault protective measures are also required. For example, automatic disconnection, extra low voltage, separation, double insulation. These are the fault protective measure. Now you also should look at this right side. There is two lines: skilled person, instructed person, normal person, skilled person, instructed person. These protective measures shall be applied in locations appropriate to the person who is available on that location. For example, the protective measure called say obstacle, you cannot make it in a place where normal people are standing. This is only for places where skilled people are there or instructed people are there. So like that, these protective measures shall be applied based on the location. You cannot apply one protective measure everywhere. Depends on the location, depends on the application, we have to select. Now, over and above basic and fault protective measure, we have to have enhanced additional protective measures which sometime offers basic and fault protection. You can find these information in part 1, chapter 10 or section 10 of National Electrical Code, part 1, section 10. Now if you read part 1, section 10, you may not be able to see this kind of a table. It contains so many explanations. If you want, I will give me a moment. Let me open and show you the NEC. One moment please, so that it is easy for you to understand and follow. Sorry, in between. So this is the NEC. I am taking the here, part 1, section 10. Now these parts, part 1, section 10, 11, 12, 13, these parts doesn't contain all the information. These parts has to be read as additional in addition to a standard called IS 732. Because if we try to put all the information into NEC, already it's 750 pages. If we try to put everything into NEC, then it becomes part 1, part 2 and non-stoppable. So you can see here, this session of code of part 1 section 10 deals with the protection against electric shock as applied to electrical installation. It is based on 4.2 of IS 732, means the clause 4.2 of IS 732 is applicable. Now if you read this clause, then you will understand that whatever written in part 1 section 10 is in addition to 4.2 of IS 732. Very important. What I mean to say is, don't follow what is written only in NEC. You have to also follow it carefully. So you have to follow IS 732 and in addition you should do NEC. Now these are the protective measures, basic and fault protective measures. The first protective measure with respect to fault, because protection from electric shock, most of the time we say it's a fault protection, because all the electrical installations, basic protective measures are already there. We are not going to get a shock from a good installation. We are going to get shock from a faulty installation. So protection against fault is always spoken as protection against electric shock. The first protective measure, if you read the standard, very important, if you read the standard must have written locations where the safety measure called as automatic disconnection is applied. I repeat, locations where the safety measure called as automatic disconnection is applied. So in several places you can see these wordings in the standard. Then you should understand that this safety measure called as automatic disconnection has got a definition. The definition is clause number 4.2.11.1, general. Automatic disconnection of supply is a protective measure in which Basic protection is achieved by basic insulation of live parts or barriers or enclosures in accordance with Annexure A. That means a place where automatic disconnection is applied means basic insulation and enclosures, that means barriers and keeping out of reach is not applied. Only basic insulation and enclosures are applied, and fault protection is provided by protective equipotential bonding and automatic disconnection in case of a fault in accordance with these clauses. It will be a little bit difficult to read and understand what is written in the standard. You should understand that one safety measure, if we try to write everywhere in the standard, only the book is going to be big. For example, clause number 4.2.11.3, it explains a particular safety measure. Now, under this clause, if you wanted to have fault protection, then you should also refer, you should make protective equipotential bonding as per clause 4.2.11.3 or 11.6. This is how it is. I hope this is clear. If you have doubt, I repeat again, in the standard, sometime it is mentioned that in locations where the protective measure called as automatic disconnection is applied. So then you should think that automatic disconnection means there are two things inside: basic protection, fault protection. Fault protection is achieved by protective equipotential bonding and automatic disconnection of supply. Just to explain you, actually not for engineers, this is for non-engineers to understand what exactly we are talking. This picture shows an installation without any fault protection. There is no basic protection. There is no basic protection means a live part can be accessible. As a result, people may get electrocuted. In the second case, an example of using enclosure, as a result, the fault protection is achieved. In the third case, the enclosure or the wire is faulty because there is no insulation. As a result, a person who is going to touch will get a shock. In the fourth case, the fault protection measures are also achieved. So this is how it is: basic protection and fault protection. Now, you get a shock from an electrical apparatus. How many kind of electrical apparatuses are there? Will we get shock from all electrical apparatus? No. Electrical apparatuses are classified into class 1, class 2, class 3. Out of this, for example, the first one, class 1. Class 1 is an electrical apparatus or electrical device in which whenever there is an insulation failure inside, the body of that part, the body of that apparatus is now energized. As a result, if somebody touches, he gets a shock. So only class 1 devices are capable of producing a shock hazard. What the manufacturer should do? And these parts which are capable of producing a shock, these are called as exposed conductive parts. The manufacturer of that particular equipment, his equipment should have a terminal, earth terminal, which we can say color yellow and green, or symbol 5019 or this kind of symbol. And the manufacturer should connect all the exposed conductive parts of his equipment to the earth terminal of that equipment. This is a requirement which is applicable for every class 1 equipment. Imagine a motor. The casing of the motor is connected to its earth terminal. Very simple to understand. If you have a panel board, body of the panel board is connected to the earth busbar of that panel board. This is the responsibility of the manufacturer of that electrical apparatus, and he has to do that. He has to have proper marking for that particular terminal. Now you are buying a motor. What you should do? You have to read the second part. Condition for connection of the equipment to the installation. Connect this terminal to the protective equipotential bonding system of the installation. Means this earth terminal of the motor has to be connected to the protective equipotential bonding of your installation. That means your installation should have a protective equipotential bonding. The second type of device is called as class 2 device. Class 2 devices are double insulated device. You can see this kind of a symbol. For example, equipment with a 2-pin plug, mostly the audio video equipment which we use in our houses, which is 2-pin. So these are double insulated device. The meaning is, even if there is an internal fault, body is not experiencing a voltage. The chance of getting shock from that equipment is nil. So you don't need an earth terminal. You can work with the 2-pin. Classic example is our mobile phone charger. But you see this one, no reliance to installation protective measure, but I have put a symbol of something looks like an earthing and a tick. This symbol is called as functional earthing. Class 2 devices may require functional earthing. Functional earthing is a subject which is not related to safety, but it is related to functionality of that equipment. Imagine you have an audio video recorder which is working in 48 volt DC or very low volt, extra low voltage. Sometimes that equipment require a functional earthing, and you can see this symbol on that particular terminal. And if you take a wire and connect it to your protective equipotential bonding, that's gone. It won't work. You need an isolated system. You need an isolated earthing. The third type of equipment is called as class 3 device. These are extra low voltage devices where the operating voltage is very small, not enough to create a shock. And class 3 devices may have functional earthing. So there are 3 types of equipment: class 1, class 2, class 3. Shock is happening from the class 1 apparatus. Now these on the bottom I have put a lot of symbols: 5017, 18, 19, 2021. These are the symbols of earthing which is applicable for different applications. All are related to earthing. The first one, 5017, is the generic symbol. 5018 is called as functional earthing. 5019 is safety earthing or protective earthing. 5020 is called as functional bonding or chassis earthing. 5021 is called as chassis equipotentiality. Then earth terminal potential closer to the functional earthing, and no protective earthing. These are the symbols which is used in the apparatus. So you should make the earthing appropriately according to the meaning. It is not like you take a wire and interconnect everywhere. Now, one moment. Yeah, as I said, the protective measure called as protective equipotential bonding and automatic disconnection of supply. I have shown you what do we mean by automatic disconnection. Automatic disconnection means there is a basic protection by enclosure or simple insulation. Then fault protection is achieved by protective equipotential bonding. And now I am repeating this word, protective equipotential bonding. I will keep on repeating because this is the first and the most important electrical safety measure. After seeing my picture, you should think whether this is existing in your building, whether this is existing in the buildings which you have designed or erected or tested. If it is not there, you can be 100% sure that your building, what you have done, doesn't have any safety. So don't think that I made a safe building. Now, protective equipotential bonding. Your building will have exposed conductive parts. You can find this explanation in IS 732, clause number 4.2.11. So you will have example, I have put sub panels, then some kind of motor. These are technically called as exposed conductive parts. Your building also have got extraneous conductive parts such as building steel or metal pipe, firefighting pipe, and so on. Your job as the designer or the contractor or the verifier is to find out you have an MET. The new word is MET. The old name is protective equipotential bonding terminal. That means you have to have one bus bar. Now, all your exposed conductive parts must be connected to MET. All exposed conductive parts must be connected to MET. This is called as protective earthing, and this conductor is called as protective earthing conductor. Sometime from the last distribution board to the socket, these wires are also called as CPC, circuit protective conductor. Basically, this is called as protective earthing conductor. Now you have extraneous conductive parts such as metal frame of your building, metal pipe of your building, maybe sewage pipe, I don't know how many type of things, air conditioner, duct and all. So these must be connected to MET independently. Independently means under any condition this connection shall not go, you should not disconnect. In future somebody making a maintenance and he shall not disconnect under any condition. This is called as protective bonding, and the wire which is used for protective bonding is called as protective bonding conductor. Then if you have a TN system, electrical systems are classified into TN, TT, IT, we will come to it in the afternoon. If you have a TN system, the MET is connected to the neutral of the transformer or the DG. If you have a TT system, the MET is connected to an earth electrode in soil. TT is applicable for low voltage electrical distribution sometime. As per our regulation, we are not supposed to follow TT, but our electrical distribution companies sometime follow TT, not sometime, almost every time they follow TT. So there is an earth electrode in soil. Regulation 16 also says even if you have a TN system, for three-phase consumers, you make an earth electrode. So basically the MET is connected to the soil through an earth electrode in case of a TT system. Then this MET is also connected to other buried metal electrodes, other buried metal parts. If you have some, for example, lightning protection system, or for example, if you have some buried pipeline and so on. This is called as protective equipotential bonding, which is the first and the most important safety measure against electric shock and electric arcing. This kind of a picture was never included in the IS standards, but CPWD manual, Annexure F, they have included this picture not only now, few decades back. This picture originated from one of the 1965 standards. CPWD they were keeping this picture and they only put this color. Now, can I ask a question? Can I ask a question? Open? Let us, we are engineers. Our job is to make our installation safe and people should be safe. Can anyone show one building in Chennai where this is carried out? Actually, I want to see a building. I am eager to see a building in Chennai where this is carried out. In Chennai, the fire department says 50% fire accidents are due to electricity. Bombay, they say 70% or 80% fire is due to electricity. Delhi says 60% is due to electricity. And if we look at as a person who is involved in the standard making, I know why these are very well written in the standard. And wherever we go, the first job is to look into this. And we don't have even one building which is satisfying this requirement. Please note that this is a starting. The others are on the way. Let me go to the second one. Any questions on this? I hope there is no question. The second one is called as, the first one, as I said, fault protective measure is called as protective equipotential bonding and automatic disconnection of supply. So that means it has got to one more part. It's a combination of two protective measures. The second one is called as automatic disconnection of supply. It means in your electrical system, you are getting power supply from a source, for example, a transformer. Then you have the point of commencement of supply, kilowatt hour. I'm sure you are able to see the cursor. Kilowatt hour stands for, the point of commencement of supply, the place where you start using electricity. Then you have the fixed part of the electrical installation or the main distribution circuits. Then you have the final distribution circuit and some appliance connected to the final or current using equipment. This is how the technical wordings are made in the standard. Point of commencement of supply, fixed circuits, final circuits, current using equipment, something like that. Now, the maximum allowed disconnection time, if we start from the equipment onwards, here on the equipment, the maximum disconnection time, Tn 0.4 second, Tt 0.2 second. That means your MCB is supposed to trip within this particular time. Tn 0.4 second, Tt 0.2 second. If you cross this time, even though you have a protective equipotential bonding, you get a shock. So the idea of protective equipotential bonding is, even if your MCB is capable of tripping, your MCB needs some time to trip. Even during that time, people shall not get shock. So you have both. So the first one, the top priority is the picture which I have shown you. Second is this one, 0.4 second and 0.2 second. Now, on the main distribution circuits, TN system 5 seconds and TT system 1 second. And at the supplier's facility, if you are a low voltage, if you are getting electricity from the low voltage supply, then it is up to, it is a national regulation. That is a different part, because NEC scope is within the, after the point of commencement of supply, after the meter board. So 5 seconds and 10 seconds, this is, or sorry, 5 second and 0.4, 0.2 second. There is some time and your protective device is supposed to operate it. Now to ensure that, there are several additional measures. These measures are, number one, the first one, we have an MCB, for example. We are going little bit into a product. We have an MCB. Imagine you have a MCB, you are not using an RCCB because you have some machines or a group of machine which is creating a leakage current. RCCBs 30 milliampere will trip. RCCBs are not used everywhere. RCCBs are used as an additional protection in certain places. You cannot use RCCB from A to Z because it creates nuisance tripping, which is against electrical usage. Now, you have an MCB, for example. Now the first thing is, there are 3 types of MCBs, B, C, D. These MCBs, the instantaneous tripping current varies. B, maximum 5 times the rated current, C 10 times, D 20 times. I am sure all of you knows this very well. Now we have to use this MCB to trip. This one, what I am showing in the picture, you can find the same picture in the NEC part 1 section 18. This is called as a TN system. The meaning, the definition of TN system is a system with a separate neutral and protective conductor throughout. Throughout means from the source up to the last socket, there is a separate neutral and a separate protective conductor. But in the future standard, neutral will be removed because neutral is required only for single phase. So the new definition will be a system with separate protective conductor. So this green wire is the separate protective conductor. It starts from the transformer neutral, and every equipment body or a group of equipment is connected to this particular conductor. Now in this particular case, imagine there is a fault. This shows, often we show this picture, this shows the phase conductor insulation has broken and it is in touch with the body of the equipment. Now the fault current starts flowing. One point you should always keep this in mind is, generally electrical engineers say that fault current go to earth. Please note that earth is not a current absorber. Earth cannot absorb current so much. No, fault current has to go back to its source. Current leave the source and return back to the source. Now, in this case, we have a protective conductor. We have a metallic fault return path. If you look at IS 3043 clause 7, it's very clearly explained. Metallic fault return path. IS 732 has written metallic fault return path. Now in the new NEC, we have made some simple pictures with some simple explanations, which is much more easy to understand. Now, the fault current is flowing through this particular closed loop. This loop is having certain impedance. Now you need a certain amount of current. Let's say you have a 63 amps MCB, and the MCB is, you have to trip the MCB in 0.3 second or 0.2 second, 200 millisecond. Then the MCB require, C-type MCB require 10 times current, means 630 amps current is required, and that current is flowing through this loop, and now the impedance of the loop decide the amount of fault current. This calculations, fault loop impedance and disconnection time is explained. For example, the word fault loop is explained in 33 places in IS 3043 and about 60 places in IS 732. The importance of calculating fault loop impedance, the importance of testing fault loop impedance, the importance of maintaining fault loop impedance. It is not in one place. It is in IS 3043, 33 places. Nowadays, a lot of, because of the, since I'm a member in the BIS, a lot of technical queries come to BIS and it is always sometime routed to me. I am seeing a lot of tenders, public, private, almost all tenders, if you start reading the earthing, the bill of material or the specification, it starts with my earthing has to be as per British, American, Indian, global, all list of standards are there. But I have not even seen one tender specification where this is mentioned. And everywhere the tender specification always say 1 ohm earth electrode. 1 ohm earth electrode. From where this has come? Nowhere in IS 3043 for a low voltage application this is written. Nowhere. IS 3043, nowhere it's written. Sorry, I am stressing it again and again because this is one of the most important points. We have an earthing session in the afternoon. Now we are talking about shock protection, but finally you have to understand and do it. Now, this one is very important. In TN system, we are supposed to disconnect the MCB and the fault loop impedance is very important. Please read the standard and understand it and do it. Now we have another kind of system which is called as a TT. In case of a fault, the fault current will flow through the earth electrode, through the soil, and it returns back to the source. Even if you maintain 1 ohm earth electrode in these two particular places, your MCB will not trip because your applied voltage is simple Ohm's law. Applied voltage is 230 volt. You have two 1 ohm resistance in series. Your total ohms itself is 2 ohms plus the impedance of the wire. So 230 divided by 2 ohm, only that much current is going to flow. Earth electrode, 1 ohm resistance and 50 kiloampere fault current withstand. Everybody go to CPRI and go with a test certificate. My metal piece can withstand 50 kiloampere. Actually, there is no logic behind it. Sorry to say that. Now, there is a system called TT. Now, in the, Mr. Bogi told the regulation number 43, irrespective of any type of system, you are supposed to use a 30 milliampere RCD in your point of commencement of supply. The new regulation 43, earlier it was 42, now it is not 43, sorry, 44. 42 was RCD or ELCB, now it is 44. It says 30 milliampere RCD is required in every electrical installation. There is a second para for this, this regulation. It says if you go for a TN system, RCD is not required. So RCD is required indirectly for TT system. Now, RCDs, there are few type of RCDs. I would like to invite Mr. Krish to explain you the type of RCDs and its application. So let me introduce Krish. As Appavu sir told, Krish is a young man of his 20s. I think he passed, he's just plus 21 plus maybe few months. Last month you had 21st birthday. But as Appavu sir told, his maturity is 60 and his knowledge is also sometime I feel 60 plus. So he is young, dynamic, and the most interesting part is he studied in not exactly in a direct course, but the UK standards he studied very well and he passed the examination from Institution of Engineers UK. I welcome Krish. Please, the stage is yours.
Thank you for that very flattering introduction. If I may just switch the slides, please. Thank you. I think everybody can see the screen, so I'll just start. Just before we begin, I'll just give you an outline of the presentation. We're going to cover, oops. Yeah, it seems so. A loose connection problem, yeah. We'll go over that tomorrow. So I'll just give you an outline first. So we're just going to recap about what Mr. GK said about protection against electric shock. and also about additional protection through RCDs. We're going to talk about testing RCDs, the RCD disconnection times when you test them and under fault conditions, as well as currents required. Then the different types of RCDs. A little more detail with that specific to IS 732 and the National Electric Code. A couple example applications, and then some load and fault current characteristics. And the last section would be minimizing unwanted tripping, which I'm sure a lot of you guys would have concerns for. So let's begin. So just as we went over earlier, these times, 0.4 seconds, 0.2 seconds, 5 seconds, and 1 second, these are for fault protection. So you've got basic protection, fault protection, and additional protection. And some of these times, like Mr. GK said, are only valid when you have protective equipotential bonding. When you have an RCD, and this is most common in locations where an installation is used by ordinary persons, you need something called additional protection. What this does is that it kicks in where you have a failure of basic and or fault protection. Or it could be just outright carelessness by user. They could plug in a device that just simply doesn't have proper insulation. And the idea is that you'd use a device that has a rated residual operating current. The current on the RCD or the RCCB, the ELCB, it says 30 milliamps. So anything less than 30 milliamps or 30 milliamps is fine. But one very important thing to remember is this is only for a dry, clothed human with no cut or open skins. If there are other considerations like a swimming pool, a special location, there are different considerations. And this will protect against direct and indirect contact. So if you can see the diagram there, you have somebody touching there's the direct contact and there's indirect contact. They're touching the live conductor or they're touching a metal part, exposed conductive parts that have become live as a result of a fault. So generally when you test RCDs, and I'm sure Sonal's instruments do this, you have to test them at the rated residual operating current, which is I delta N, and 5 times I delta N. And you have to do this at the positive and negative half cycle. So when the sine wave goes up, you have to do it there, and when it goes down. So that's a total of 4 tests. And the trip times should be lesser than or equal to 300 milliseconds for I delta N, and lesser than or equal to 40 milliseconds for 5 times I delta N. Now why these times, and why 30 milliamps? So although this is not really useful for someone who's an electrical engineer, I'll just give you a little bit of context. If you see the red dotted line and the red line, we're in AC2, that is 300 milliseconds and 30 milliamps. And AC2 is, the shock is perceptible, but there's no muscle reaction. Oh, the cursor right, yeah, that'd be nice, thank you. Perfect. So, sorry. So if you can see this, where the laser pointer is, that's 300 milliseconds and 30 milliamps. So that we're in zone AC2. The shock is perceptible, but there's no muscle reaction. So as some of you may have had the misfortune of actually experiencing an electric shock and an RCD was protecting the circuit, you would have realized that you did feel the shock before the RCD disconnected. I've been one of those people. And then where the blue line and the blue dotted line intersect, that's 40 milliseconds and 150 milliamperes. So that's 5 times I delta N and 40 milliseconds. And again, you're restricted to AC2, which is it is perceptible, but there's no muscle reaction. That's why 30 milliamps and these disconnection times, and that's why you verify them. Now the types of RCDs. I'm sure 99% of you sitting here would have installed type AC RCDs. I'd be very surprised, and I'd be more happy to know if you've installed type A's, F's, or B's. Now, from a manufacturing standard point of view, we have IEC 61008, which does type AC, or the equivalent Indian standard, which is 12640 Part 1. And if it's an RCBO, it's going to be 61009 or 1260 Part 2. And these will only react to faults where you have residual currents that are sinusoidal, which exactly mimic the sine wave. But as all of you are aware, most of our loads nowadays, including this computer and this screen, do not work on pure AC. They work on pulse DC, DC, and in case of an inverter air conditioner, a completely different form of AC. So then we have type A, also covered by the same standards, but it can do pulse DC. So a lot of LED lights, they use a bridge rectifier or even a simple diode to result in pulse DC. We'll look at that in the next slide, the different kind of waveforms. Then you've got type Fs, which is a completely different standard. There is no current IS standard for this. It's 62423, which is the IEC standard. This can do everything that type A and AC does, and it can also do residual current, so that's an earth leakage current that is between 50 hertz to 1 kilohertz. So then if you have a frequency converter, a VFD, an inverter AC, this kind of an RCD takes care of that as well. A type B RCD, which a lot of you would have heard about being used in EV applications, does all of the above plus smooth DC. And the limit for smooth DC before it trips is 10 milliamps or 0.4 times I delta N. So in the case of, whichever is higher by the way. So in the case of a 30 milliamp, that's going to be 10 milliamps or 0.4, which is 12. So 12 milliamps is going to be what it is. But in the case of a 100 milliamp RCD, it's just going to be, it's going to go higher. So, but in a 10 milliamp, it's lower. So you get the idea. That's just the manufacturing standard. Now, just going into further detail a bit, this is an excerpt from the National Electric Code. If you look at Part 1, Section 10 and Regulation 5, you'll find this in greater detail and a couple more limits. I'm not going to go through these because we get the idea from earlier. Same story here. Now, when it comes to actually specifying these, what do? By far, your minimum specification should be a type A. Type AC should not even enter the picture. Because just think about it, LED lights, pulse DC, inverter, air conditioner, different frequencies altogether. And if you have a 3-phase air conditioner, which is then going to use a 6-pulse bridge rectifier and then going to create a completely different frequency, a current of completely different frequency, then you're going to need a type B RCD. So again, I'm not going to go into depth for this because we're not electrical appliance manufacturers, but as you can see, there are only 2 basic circuits where type AC would work, which is a simple phase control, which is like a dimming circuit, and a burst control, which is a similar circuit where you can create pulses used in some motor control circuits. The moment you have a simple diode and a load, just like in an LED light, immediately you need a type A. Type AC is no longer usable. It will stun. Then, let's say you got a 2-pulse bridge rectifier. You rectify it, and so similar story. We're using pulse DC, type A is still fine. Now this is where it gets interesting. You have a frequency inverter, that's your inverter air conditioner. First you create it to DC, goes through the full bridge rectifier, gets smoothed out with that capacitor. Then you may have a load there that works on smooth DC, and then you have an inverter, which goes to a motor, which could be the compressor in your air conditioner. Immediately here, because we're dealing with frequencies other than 50, 60, or 60 hertz, we need a type F. Then when you go into smoothing or just smooth DC without an isolation transformer, the waveform looks almost pretty smooth. So again, a type F is not going to work here. You need a type B. Going further, as the inverter circuits get more and more complicated, type B is going to be what you need. And what's beyond the scope of this presentation is pure DC, and that's a completely different type of RCD. It's not even called an RCD. And the last thing is number 13, which is a simple 3-phase frequency inverter, and that, so you have a 6-pulse bridge rectifier, converts it into DC, smooths it, and then you have an inverter. That is basically any large inverter air conditioner circuit, that's what it's going to be like. You need a type B, if an RCD is required as per 732. Now, unwanted tripping is a big issue. So I'll give you a classic example. I was designing this site in Mumbai, and they had about 11 VRV air conditioners. And when I went to meet the air conditioner manufacturer, what they told me was, RCD, RCCB or AC साथ में नहीं जाता है. For those of you that don't speak Hindi, that means RCDs and air conditioners don't go together. But that's not exactly true. What they were referring to was the fact that because of poor installation methods, which I'm going to get into my presentation tomorrow, there was a lot of leakage current that was being created. So given that you have a perfectly well-installed system, you need to ensure that your RCDs are not leaking less than 30% of their rated are not leaking more than 30% of the rated residual operating current. So for a 30 milliamp RCD, that is 9 milliamps. Now you might say in a perfect installation, why would you have leakage at all? The truth is, most electronic circuits have something called filtering. There's a great article on this, I can share it with you guys later on. But as a result of normal operation, electronic devices will result in a certain leakage to earth. And that is what an RCD picks up as an imbalance, because we know the RCD works on a residual current principle. One of the easiest solutions for this, and which is what's been adopted abroad, is that they just use RCBOs for final circuit. So every final circuit, a socket circuit, a lighting circuit, has got a 30 milliamp RCBO, and the overcurrent device characteristics are just as per 732, 4.2, as Mr. Gopakumar said. And it's also quite important that you can't use a type B RCD just for an EV charger, and then an upstream RCD, which is an RCD closer to the meter, cannot be a type AC or a type A. This is because that RCD will not be able to react to the leakage current created by the load requiring a type B RCD. So when you're designing an electrical installation, selectivity and specifically breakers that go upstream and downstream, they make a big difference. Lastly, I just got this Venn diagram here. See, most electrical installations in India are cheap and usable. They work until they don't, and they're really low cost. That's where most electrical installations in India are. Safe and cheap installations exist, but most of the times they're not practical. Like imagine if I take 130 milliamp type B RCD and put it on this entire center. Great, it's going to work, it's safe, it'll trip. But what's going to happen is, the moment you have an earth fault, the 30 milliamp is going to exceed and the entire building will lose power. It's difficult to use and it doesn't work. Lastly, you've got safe and usable, and that's where we need to be. And if you see in the middle, safe, usable, and cheap is not really possible. I'll just end with a quote by a friend of mine, Dex Whitmore. He's credited to Sir James Reason. It says, if you think safety is expensive, just try an accident. Thank you.
So thank you, Krish. We go to the next part, which is, it's actually a continuation. We are only breaking sometime, otherwise, if I alone speak, you become bored, because all of you are, just looking at the board or somewhere and no one is speaking and no questions. Generally, we are in a technical presentation, in a seminar, even if there is no question, absolutely no issues. But in a technical presentation, if we get more questions, then only it can be an interactive session. So I request, please stop me in between, and if you want any questions, we can discuss, clear it, and then go to the next part. Now, let me go to my presentation. One moment. So basically, RCDs, how it works, let me skip. RCDs are of 4 types: type AC, type A, type F, type B. Modern electronic devices, type AC, which we generally use, or nowadays we have to say that it is not actually the right one. We have to use minimum type A RCD, because we have a lot of LED lights and devices using DC. For smooth DC application, for example, rooftop solar PV installations where the inverter doesn't have simple separation, we are supposed to use a type B RCD. Similarly, for a variable frequency drive, which is of 3-phase variable frequency drive, we are supposed to use a type B RCD, because these, either solar PV or the variable frequency drive, the chance of DC leakage current is also there, or DC leakage current exists, which can also create shock hazard and which can also kill people. So we need protection against shock by these RCDs type AC for one application, purely AC application, type A, type F, and type B. Now I ask another question. Sorry to ask so many questions. If I wanted to, I have a solar rooftop in my house. I want to buy a type B RCD. Is it available in Chennai? nowhere in India.
Yeah.
True.
So I was going to ask a question on that. So are the manufacturers ready to adopt this? Because they have to adopt this and then it will be available across.
Yes. Actually, sir, for this program, we need to have some manufacturer who are the switchgear because very important subject. They have to tell.
Some of our colleagues from our switchgear people are available here, so they can take note of it.
Yes.
Okay. The L&T switchgear, which is now with Schneider, those people are available. So this needs to be changed because as he presented, type F and B is not available presently, I suppose.
Yes, as I told, I show you how it is written. This is the part 1, section 10. So here the the type of RCDs are explained at AC, A.
It's not yet come.
Oh, sorry. Can you put my screen? Sorry, 1 moment. It's my mistake. Yeah. Now, this part, this is part 1, section 10. As I said, part 1, section 10. First, we need to understand IS 732 and whatever written is additional. So, here you can, if you scroll down, you can find out the type of RCDs explained, type AC, type A, type F, type B. So, this is type B. You see the wording, RCDs of type B shall be used in case where the application may create smooth DC residual current or contain frequencies higher than 50 Hz. For example, 3-phase class 1 device containing a motor controlled by a 3-phase variable frequency drive. This is the case of certain type of 3-phase air conditioner or pumps or even supplying an electric vehicle. Please have a look at the word shall. RCDs of type B shall is mandatory. But before writing here shall, we had a big discussion. Because if the product is not available, how can you write shall? Then finally the committee decided whether the product is available in India or not is none of our business. Our business is to write a code which is making the installation safe. Whether to supply or not is none of our business. So it is the suppliers and between the supplier and the user. Now if you cannot make it, you go for a proper TN system. If you go for a TN system, you don't need it. Very simple. So,
yeah, one more question I had. What about the 12 pulse? I think he showed it for the 6 pulse.
yeah,
12 pulse, anything else?
I think it's type B.
Type B.
Type B. F.
If you like, we can have a discussion about
Yeah,
slightly.
yeah.
Thanks, Krish. Thank you, sir. So I think you are all are looking seriously hungry. It's already 1:58, 2 o'clock. Shall we break for the lunch or continue? Because after my first question, can you show a building with the protective equipotential bonding? Then I could see a lot of angry faces on me. I wanted to go for lunch at that time. Please.
No, we are all trying to do good things for the country, so I think it's good.
So let us break for the lunch and shall we? Okay, let us break for the lunch and join back at the earliest because we have a lot of things to discuss. Actually, we are already half an hour or 1 hour late. Let us come back quickly. Then we will start with the second session, thermal effect. Thank you. All of you know the difficulty in opening the eyes, keeping the eyes open after lunch. And that itself a good lunch. Ear is open. But that's not enough. On the slide, some pictures are also there. So, actually before starting the session, next subject, thermal effect, I would like to go back to the first subject again to show one part. Please don't think that by making protective equipotential bonding, that's all about shock protection. No, shock protection, there are so many measures. I explained only one. I would like to explain one more measure which is important in today's context. What you are showing is protective conductor current. See, in the electrical system we have current carrying conductors or live conductors and protective conductor. Protective conductor, or called as earth conductor, generally should be a dead conductor. It is not meant for continuous current flow. Ideally, zero current should flow. But as Krish told, due to the inherent characteristics of today's electronics, because of the filters, there is a leakage current flowing through the earth conductor. Now, if there is it's not a short time current flow, it's a continuous current flow. Now, if there is a continuous current flow through the earth wire, which is more than certain limit, this will lead to fire. Fire, arcing, shock, and a lot of problem. The safety measure is you must ensure that the current, continuous current through the earth wire must be limited to less than certain level. What you are seeing in the screen is, for a typical case, for example, up to 2 amperes load, 1 milliampere leakage current. For anything more than 20 amps, the line current is more than 20 amps, the maximum allowed leakage current is 10 milliampere. So this is actually a very important safety measure against shock. As I said, on the list has several measures. One is protective equipotential bonding, automatic disconnection. Next, one of the safety measure is this. Why I show this is, if you look at the IE rule since 1956, IE rule after it has become the CEA regulation 2010, there is a regulation which says at the point of commencement of supply, once in 5 years, we are supposed to, not we, the energy supplier is supposed to measure the continuity resistance, the insulation resistance test, and the minimum insulation resistance is 1 mega ohm. Once in 5 years, we are supposed to do it. From 1956, it is still there. Even 1956, even before that, there is a 1937 rule. So even in the 1937 rule, the values were different, because 1937 rule, the term voltage was not existing at that time. Instead of voltage, it was called as pressure. Voltage was once upon a time called as pressure. So the insulation resistance maximum allowed, minimum insulation resistance should be 1 mega ohm in a low voltage installation. If you maintain that insulation resistance, this leakage current, it's an indication that the installation is free from leakages. Now, some of the modern equipment such as UPS, variable frequency drives and all, they have a leakage current more than this level. If the leakage current is more than this level, we may have to put additional safety measures. Reinforced protective conductor. Sometimes the protective conductor is having a higher size, maybe one more terminal. To stress this point, there is one more subject. Nowadays, especially electronic engineers, instrumentation engineers, normally they have some kind of noises and related problems. One of the solution which people think that there is a gadget available in India which is called as digital earthing system. It looks like a black box, and the vendor says if you buy this product and install this, all your problems are gone. So even in our India's some of the prestigious government organizations for instrumentation system, these devices are installed. Once when we measure the current, instead of 10 milliampere, the current is sometimes 99 amps. So it's a violation of safety. So please keep this in mind. So like this, there are several measures. If we keep on explaining, it is a big subject. Now regarding thermal. As I said, for the shock protection, there are two concepts, whether you can trip the supply or you need the continuity of supply. Similarly, with respect to thermal effect, this one gives the fundamental idea. You can see on the x-axis, you can see the time, and here on the y-axis, you can see watts. This power watts is nothing but the heat produced because of a fault, or because of, say for example, due to the device operation, some heat is produced, but due to some abnormal condition, additional heat is produced, for example, which is coming onto the surface of this particular equipment. So surface is becoming hot, and that particular heat, finally we have to find out how much wattage of heat is there, or leakage, or due to fault how much heat is generated. Now if the equivalent heat produced is lesser than 15 watts for a longer duration, the heat cannot produce fire. If the heat is between 15 watts to 100 watts, ignition under some chances, ignition is possible if under some conditions. If the heat is more than 100 watts, then gone. So it's a sure shot fire. Now, under some, if some ignitable things are there, yeah, on the location or on the surface of the equipment, then it catches fire. Now similarly, with respect to the maximum power dissipated because of the heat, whatever the maximum power, let's say 1 kilowatt or 2 kilowatt, if the heat produced is limited to less than 15 watts in 3 seconds, then the chance of fire do not exist. If the heat produced is limited to less than 100 watts in 5 seconds, then the chance of heat is only under some condition. If it goes to the red level, more than 100 watts, more than 5 seconds, then the heat is sure. Based on this concept, electrical power sources are defined. Power source in the sense, imagine you have an air conditioner which is catching fire and it started burning. From where the power is coming? Power is coming from the source. It is the source which is feeding further energy to heat up the equipment. So if the power from the source is limited to less than this level, then the chance of fire is less. It's one of the idea which has gone into making the standard. So this level, for example, is maximum limited to 4 kilowatt. And the power supply source PS1, PS2, PS3 are classified, and based on this is one of the criteria for selecting the wiring condition, the wiring rule, especially conduit wiring. We have the MCB-DB, finally we have the light fitting fan, the rating of the MCB, and the distance of these the wires, and finally the connected equipment for domestic and office use, not for industrial purpose. So with this concept, further the fire things are defined. I just show it only to give an information to you. One of the concept idea which also has to be explored in India, probably in the next national building code, is building classification with respect to evacuation. What the IEC says is, with respect to electrical, buildings are classified into 4 categories, BD1 to BD4, with respect to evacuation, because during the evacuation, electrical safety services should work so that the people can be evacuated. So there is a time specified by the national regulator or by the national standards body. With respect to electrical, there are 4 categories, BD1 to BD4. Now if you look at the standard has written IS 732, authorities responsible for building construction, public gathering, fire prevention, etc. may specify which BD condition is applicable. Who has to specify this is the local government. For example, in Chennai, the municipality or whatever, they have to specify the building of this much height and this much size and this many people has to be categorized as BD3 or BD4. That is the responsibility of the municipality. Now, what the electrical safety standard gives is, for example, in condition BD2, BD3, BD4, wiring system shall not encroach on escape route unless the wiring within the wiring system is provided with a sheath or enclosures provided by cable management system itself or by other means. So basically on the escape route, the additional safety measures required on the escape route or for the fire safety services are specified in the standard. It is not only one method, several methods are there. Where you can find this information is IS 732 clause 4.3. If you want to see the clause, I will show you. Just a moment, please. So this is IS 732, clause 4.2 talks about the protection from electric shock. Yeah, this is the 4.3. Protection for safety, protection against thermal effect. So this clause very well explains different methods which has to be applied. For example, you see here, in condition BD2, BD3, BD4, wiring system that are supplying safety services shall have a resistance to fire rating either the time authorized by the regulation for building elements or 1 hour in the absence of such regulation. That means fire resistant installation is required in these categories. Then each of the items, like for example, wiring system in escape route shall be as short as practicable, and that means the length has to be as short as possible, and shall not be flame propagating. Then the requirement of the cables, support system, fixing materials, all are given. This means the wiring which is on the escape route has to satisfy these requirements. So like this, there are several safety measures included in clause 4.3. Tomorrow we have a session about the selection of wires. Probably we, yes.
ISIEC code is that is 61936. It is
Yes.
available.
Yeah.
Not only in NEC 2023, it is available in NBC 2016 also. It is in part 4 annexure C. It is available.
I know that. I am a member in that committee.
Yes, sir.
it
It
is
is
there.
that what I am saying actually, fire prevention, actually it is available in 2023, it is also well explained there actually. See, there are 3 things. One is actually, fire should not spread from one compartment to another compartment.
I am
What
coming
are
to
the
that
sealants?
point. I only started now.
Started, okay?
Yeah.
Oh, please.
I am
Okay.
coming to that point.
Right.
Tomorrow we have a separate session on wiring, fire compartmentization, then fire sealants and so on. What I am saying is, building is classified into various,
Okay.
based on the first is classification.
Okay.
Then based on the classification, you find out what kind of measures are required for your building. First you classify, my building is BD4, it's a high-rise building, 10 floors, hospital. So first is BD4. Then you find out from this particular standard, you find out the requirements of the, it is not only about fire detector or fire sealant or something like that. It starts from the source. You have to have a source which is capable of running even under fire.
Yes.
It is about the light fitting, finally this also should work.
Yes,
So if we look at the entire scenario from the source, from the wiring, from the through the distribution board up to the last light or whatever, fan or the smoke extractor or whatever, everything should work. So those are there actually, very well included in the standard.
Yes, sir. Actually, in the standard, no, they have explained complete building also. What are the building types, what are the fire prevention method we need to install, especially actually prevent the fire from one compartment to another compartment, then how to protect the emergency escape route, then the functioning of important electrical system during fire emergency, it is also available.
Yeah, what we tried doing is, for example, in one area, which is part 1 section 17, I'll show you where this is connected. See, NBC has classified building into something.
Like it is available in IS 2190,
Yeah.
different types of buildings.
So,
The different types of fire resistant material, no, it is fire reactant material, it is available
we are
in
not,
EN.
we are not talking about all those things. That
Yeah,
is none of electrical engineer's job. Electrical engineer's job is you select the wire which is tested as per the standard and use it as per the standard. That's it.
Sir, one more thing I'm telling you
Yeah.
actually, any building, even if you install electrical installation, 4 shafts are unavoidable. You know, this electrical shaft, plumbing shaft, then bus duct shaft, then another pipeline shaft actually. In the shaft actually, if any fire happening in one floor, the fire should not spread to another floor, for which you need to give a sealant. So it is also coming under electrical only. After doing your bus duct installation, running main installation, the fire sealant is required. It is also there.
Yeah.
Can I
think we are-
repeat?
Yeah, 1 minute.
Can I repeat what is written in the or followed internationally?
In the, yes, NEC
Now-
2023, they have allocated, actually ISS adopted on IEC standard, it is IEC 61936, it is mentioned in 2023 NEC.
Correct.
Under this, all these informations are coming. You tell actually.
No, but
because
I
it is
didn't understand
in
the
IS
question.
732 only you tell actually. It is not in IS 732. It is different IS code. It is available.
So one second, sorry to intervene. What you say is 100% right, we agree. See, IS 61936, it's not in 2023. It is amended in 2021. And
NEC 2000.
Not NEC. IS 732 have come into effect in 2019 itself. The purpose of we engineers should refurbish ourselves with reference to the parent standards, which it is derived. So IS 732 2019, the particular part with regard to IS 61936,
Correct.
part 1,
Yes,
2021,
yes, it is.
will become wide. We have to refer that standard. In my deliberation, you will
Yes.
explain. Another thing, regarding fire stop, it is detailed in regulation 36. Now, I think the regulation number is
Yes,
changing.
yes.
Regulation
CD 36 it is, correct.
See, there are several measures have been incorporated, especially under the head multi-storage buildings.
Yes.
So let us allow him to
Okay.
finish it.
Okay,
Then
okay.
subsequent sessions,
Right.
I will explain IS 693, over voltage, everything.
Okay.
Then regulation is already there.
Right.
Sorry
right.
to do.
Okay, it's all right. Please continue.
Can I continue?
Yes. you can.
Yeah, thank you. Sir, what we are discussing about is the thermal effect. It is not only about fire, because before fire, the material starts heating due to some reason. So the idea is this heat which is produced in an electrical appliance or in the wiring, it shall not become a fire. So fire, yes please.
Requirement. Is it made mandatory or it is still an option of the consumers to choose?
If you give time, I will explain. It is there.
Yeah, sure, you can make a note of it and answer later also.
No, one thing, I think he's covering all those things in the subsequent things.
Yes, all
Okay.
these are there. in
Yeah,
the
now what
subsequent
he's
slide.
trying to explain here is thermal effect. Are we doing a study for thermal effect and implementing the wiring or whatever protective devices to take care of that from fire to come at all first? If you
Yes.
solve that, the fire, okay, if at all beyond this it comes, there are various methods as that gentleman said.
You see,
Sealant, everything is the next level of passive protection. So I
Yeah.
think some of the questions you're asking is coming subsequently, the answers
Yeah.
are coming subsequently.
so the idea of showing this slide is, normally we think what exactly it is. You should think that if the MCB or if the problem is tripped, if the protective device is able to trip within 3 seconds, then there is no problem. We are not talking about 20 millisecond in the previous, 200 millisecond in the previous case. Here, you see here the time, within 3 seconds, you have to limit the power, the heat to less than 100 watts. If the MCB is capable of tripping within 3 seconds, still we are safe. A fire from an air conditioner means the MCB didn't trip even for 3 seconds. So this is the first measure. The protective device should trip within certain time, not after some time. Now, if the MCB is able to trip within that time, you have no chance of fire. That should be the way. It's a preventive measure. It is not a good idea to not to have these preventive measures and look at all the fire protective measures. That is not the right idea. First is all these preventive measures should be there. Next is, even if after all these safety measures, if a fire comes in a building, then we have to have all the protective measures. Now, mounting. There are some appliances which is arcs or sparks may be emitted in normal services. There are some appliances which creates arc internally. There are some appliances, for example, equipment causing high temperature. If during normal operation, if there are some equipment which is creating heat, you have to mount it in such a way that the heat is not, it is not creating trouble to the nearby equipment. So mounting instructions are there. Then for equipment, those who are creating arc, those requirements are also given. The fire categorization is given. You please read here. Safety services may be required to operate at a relevant time, including during a main and local supply failure and through fire conditions. To meet these requirements, specific sources, equipment, circuit and wiring are necessary. It is not about one item. It is not about, for example, not only about wire. It is starting from the source, through the equipment, through the circuit, it is finally to the wiring and all the equipment. Each of these equipment, each of these items should offer certain fire integrity. All these are included. And this particular session, why I mentioned IS 732 is, if you go to the NEC, Part 1, Section 11, which is fire protection or thermal effect. Now let me take that and show so that you are clear. So this one is section 11, protection for safety, protection against thermal effect and protection against arcing. So now this section of the code part 1 section 11 deals with protection against thermal effect. It is based on 4.3 of IS 732, means the clause of IS 732 4.3, which is a basic safety standard that applies to the protection of an installation from thermal effect. Additional measures required are explained in this session. So the basic fundamental things in IS 732 are you must follow, and whatever explained in NEC must be made additional. The point is, if you avoid what is written in IS 732 and follow only what is explained in the NEC, then it's a problem. So the idea is to inform you that this is how you should read. Now, yes.
We talk about thermal effect. Thermal effect normally more available within the panels. What are the protection devices suggested thermal effect for mainly for the panels? What standard says?
That is the panel standard.
No, what is the thermal effect protected device standard says?
For example, if you are using I think some kind of plastic material, it is about 70 degrees maximum allowed. In some other case, it's about,
due to very reason, within the panel, thermal effect are being generated, mainly for loose connections. Secondly is that, from MCCB, heat dissipation is there, particularly busbar loose connections. There are various reasons are there. Normally it happens, generally it happens. So what is the standard says to give effective protect device?
More than 70 degrees, you are not supposed to operate it. If due to some loose connection, if the temperature is more, you should switch off, then tight it, make it pakka and then run it. That is the only way.
Sir, we will not have any protect device. Once it senses above 80 degrees centigrade, at 90 degrees centigrade, it can trip the incomer breaker or something like that. Is there any device? Is there any standard says?
There are some devices. Because in day before yesterday we had a program in Delhi. There was some sponsor who was showing, I think Schneider. They were showing some product which is like a PTC which can be connected to the bus bar. Once when the temperature is beyond a certain limit, they are supposed to switch off. It is there. I don't know who has displayed.
Only indications are there.
No, you can do whatever you want. You get an indication. You can switch off or put it to the BMS or whatever.
Arc is there, which can avoid that all you are saying, what are talking about.
Right. Sir, again, sir, Jensen, you know, the issue what I am talking is a serious issue available in the most of the installation. Automatic fire suppression system is there as one device recently been introduced. Can it not be made it mandatory for all the panels, which can take care of this thermal effect on the panels?
Sir, you can handle it in two ways.
Is there government authorities, can it be made mandatory?
Yeah.
See, it's available in the NBC right now. You'll have to have that gas suppression for main panels and critical panels like lift and other things. Probably it's not extended to all the areas, but how probably we have to interpret is all the, like wherever he's saying fire safety areas, probably those sort of panels should have this compulsorily. I mean, that's how we should interpret the code. Probably some more clarity will come in the next NBC or...
Sir,
That's
you
what
can...
they're already insisting now on NBC.
No, sir, please note that you can handle it in two ways. If you know that your panel is going to have high temperature, first is you know, then you rectify. If you don't want to rectify, then you put whatever the suppression system or something like that, they are going to...
No, that's what he's explaining in two ways. One is this testing, whatever testing they're saying, making it mandatory every year. You can come to find out certain things like this and rectify. That is one way of doing. But the other way is, as NBC specifies this for main panels and other things, use gas suppression wherever this heat goes up. You have the suppression system working to protect the fire.
But
so these are the two ways.
Suppression system is not a proactive measure. It's not a proactive measure. Suppression system knows, for example, I am putting suppression system in my panel. First, I am not confident about my panel. Am I correct?
That's a point.
So if I am not confident about my panel, then why do you buy my panel? You go to somebody who is making a good panel which is not producing heat. Simple.
He's got a point there because all the panels... all the panels... No. What is the thing is, there is a... One minute. No, we are not testing the temperature build-up in a panel in the factory or whatever it is. That is something, that's the point he's making. If your panel is rated for 70 degrees centigrade, it should not exceed. By using your panel design or the components you choose within the panel, it should not exceed. And that's how it is to be tested. Any other views? Yeah.
Sir, can I? Yeah. Okay. Now, what I am showing in the... Oh, sorry, it is vibrating. What I am showing is the testings which are mandatory in a installation. For example, these are the tests. As I said, it is not introduced now. It is since 1989. Almost 33 years back it is included. Continuity resistance of conductors. Of course, this is not for the entire thing, but for the final circuits and protective conductors. Means, after installation, you have to find out the resistance of your wire including termination and find out whether it is lesser than the allowed limit or not. Then, for example, this automatic disconnection of supply, earlier it was fault loop impedance. If there is a heat is either undersized due to the undersizing of the conductor or bus bar or due to loose contact, major two reasons. Now, if there is a loose contact, with this test you are able to find out, and this test has to be, your system has to be put into service after making this test, and if you are not making the test, it is not the fault of the standard. But now we know that we didn't make the test and find out and rectify. We know that tomorrow this panel is going to catch fire. Now putting fire suppression, that is one way of thinking. The correct way of thinking is you do the test and find out and rectify. Actually, you are supposed to run the service after complete pass of this particular test. And if you do that, these problems can be solved. Not only this, lot of problems can be solved. We will cover it tomorrow actually.
Active and passive fire protection. Active means you are giving some system for once the fire will happen, you have to quench the fire. For that, you are doing that. But what he is telling is the passive fire protection. In your system itself, you have to inculcate the protection system. That part only is telling. Correct, sir?
No, sir. I am telling that electrical system shall not produce more than certain temperature. The electrical system shall be designed, erected and tested in such a way that more than certain temperature under normal condition or under fault condition or under short circuit condition shall not happen. So the fire is after that, but before that itself you trip the system. Now, yeah. Yeah.
Bus bar on the panel, various other options. So it's the complete ecosystem. Yes, the standards are there to actually ensure that we follow. So it's not, shouldn't, I mean, my opinion shouldn't be seen it in one way. It should be the complete ecosystem, standards, maintenance, monitor it, and then ensure that the, these issues don't come out.
Yeah. Now, for example, you have a panel which is risky, or you feel that it is risky. I have made all the tests, all the things. I am 99.99% or 90% sure that it's safe. Still, if you have fear, because this is such a large building, the fire can be disaster, then you can go for all the additional measures. And then with respect to fire compartments, there are two things going on. It is the fire, the person who designs the fire protection system, he has to categorize the sections of the building. For example, you have a shaft. What the electrical standards required is any entry. Now first you think that this shaft is one area. It is categorized as one location. The entire shaft, for example, from the ground floor up to the 20th floor is one category. Where you should seal the entry into that shaft and the exit from the shaft. These two places, entry into and exit from the shaft, if these two places are sealed and if you think that this entire shaft is one location, you are done. You don't need to make it every floor wise. The second way of thinking is, I don't trust entry and exit, let me put sealant in every floor. That is another way of thinking. Whatever the way, it is up to the designer to do it. The standard is in that way flexible. So first the designer should decide what kind of categories you want. I hope it's clear. Beyond certain limit.
Design is there, then where is the question of this? Unless there is, as you say, some faulty connections or loose bolts or something
No, that also the chance is less, sir. For example, these standards are made with such a care that even if somebody makes a fault, system should trip. Even if the tripping mechanism is not working due to reason, then only the other things start coming. This is what I told. Some of the panel board manufacturers, they have some thermal sensors on the bus bars. Yes. No, this is what I told in the first part. This is what I told in the first part. There is some, coordination problem between the electrical standards and the NBC standards. What is adopted in this NEC is from the IEC 60364. Now NBC is not only this part. I can find out 100 such, synchronization problems. We will probably in the next NBC, which is the revision already started, all these points will be discussed and rectified.
I think the NBC next edition is 2025. I
Yes.
think all the points can be collected and presented to them to be a coordinated NBC.
Yes. So thank you very much. Now, first of all, thanks for all these questions, because otherwise, the mood was to go towards, it was going down, and then suddenly it becomes with a lot of energy. Now, Mega pardon? Yes, all eyes are open. I have something to discuss about the wiring system as well. This anyway, tomorrow we have a session on wiring system, we will cover that. Now, a new subject for fire protection, especially which is called as AFDD, Arc Flash Detection Device. For this presentation, I would like to invite Krish to come and explain. There is a device called as Arc Flash Detection Device, because in a good electrical installation, where overcurrent protected, earth fault protected, and all the conventional safety measures are already there. Now if there is an arcing, either series or parallel arcing, there is a chance of fire, and these devices come into rescue. These are called as AFDD. This is included in the part 1. I will just show you where it is included. Part 1, section 12 of the NEC. Mega pardon? I will show you. Where is it? Okay, now for shall. Arc flash detection device shall be provided for single phase AC system with an operating current, single phase up to 63 amps, this is not existing, but there is some reason to put it. In premises with sleeping accommodation, bedrooms and habitat. Now let me, Mr. Krish, you can explain about, you use the mouse.
Hi everybody. From feedback I received earlier, I'm going to go slightly slower this time. So, yeah. Okay, so like Mr. Gopakumar mentioned, we have AFDDs. Has anyone here, show of hands, ever held an AFDD or even installed an AFDD? Okay, so you're saying you're unable to buy AFDDs. So, should it? Let's hold that thought. So, the format I'm going to do is frequently asked questions, because you get a lot of questions on AFDDs, so I thought I'll break it up into a couple questions that I get frequently asked, and also I've seen people ask in a public forum. So, the first thing is, what does an AFDD protect against? We all know it's an arc fault. So what causes an arc fault? What does an AFDD do? How does an AFDD work? What about my other protected devices? Basic protection, fault protection, additional protection, and what about those? What kind of AFDDs are available, like the gentleman mentioned? What does SP30, our National Electric Code, even say about AFDDs? And are there any other considerations? So, what does an AFDD protect against? Now, do you guys recognize that terminal block there? Have any of you guys used those terminal blocks before? Show of hands. Seen them? Yeah, okay, good amount of people have seen them. Do you actually know that those are meant for heating control panels and they're actually supposed to be inside enclosures? They're not supposed to be like that. But very often electricians in India will use those to extend wires. We'll get into that a little more tomorrow, but that's a very common reason for an arc. Say you make a bad connection there and then the current jumps. What happens when the current jumps is actually a vicious cycle. So there are two kinds of arcs. There's a series arc where you have current jumping between two parts of the same conductor, so a poor connection. So line goes to line ahead, not line to neutral. Or a parallel arc, which is usually caused by material damage between two conductors. So you have a live and neutral, and there's a small, let's say, a hit by a nail or something, but it's not enough to cause a short circuit, but the current jumps. So that's a parallel arc. And another interesting thing about AFDDs are, they're heavily based on electronics because the technology is dependent on monitoring waveforms. So an AFDD will actually trip at sustained overvoltages greater than 275 volts. And that, interestingly, is not, well, for a various bunch of reasons, is not a substitute for an SPD. It is actually simply to protect the electronics inside it. And the basic point that AFDDs were introduced for is arcs will eventually lead to fires, and which is why they're part of 60364-4-42 and section 4.3 of IS 732. So we'll just look at the image there. Say you got a damaged or loose cable. What happens? You get an electric arc. Now most of you guys, do you use PVC? Do you use XLP? So for PVC, how many of you guys use PVC as a default for all your specifications? PVC cabling. Nobody uses PVC anymore?
Nowadays, PVC is, we've gone to the next levels, XLP. And
so XLP.
Yeah.
So great. So that's interesting because XLP, unlike PVC, doesn't carbonize. So the risk is lower, but it's not gone. So with PVC, carbonization happens, you have a fire, and then the current jumps, and it keeps going on and on and on until the current is enough to actually be a short circuit. By that time, a lot more damage would have already happened. So what causes an arc fault? Seemingly mundane things like an electric socket mounted too low. Any of you guys seen that? An electric socket mounted so low that you're trying to plug your laptop in and the cord gets bent. What's going to happen inside? One of your conductors might just snap. It might be a poor it might be a poor connection, and then you have a series arc fault. Now, any thoughts on whether MCBs, RCDs, fuses, MCCBs, anything is going to pick this up? Anybody? Okay, maybe I'm asking too many questions. Similar thing, terminal block. You have a damaged conductor there. It's going to jump. You drill through a cable, but you don't damage the insulation enough for a sustained short circuit. That's going to result in an arc. You have a socket outlet with a poor connection. Now this is really interesting because Sonal mentioned loop impedance testing. So it's at my own office actually, where I bought a fridge and it kept behaving very funnily. So what I did is I retested the line to neutral loop impedance and I got 10 ohms. Now typically for that kind of circuit I was expecting something like 0.66 ohms. So 10 ohms was clearly indicating a bad contact. Now over time, if it was a bad contact, the current would jump depending on the nature of the contact, especially on non-ISI marked sockets and those multi-pin things that are extremely dangerous. I'm sure you've all seen those. Or just a simple loose connection like a gentleman was mentioning. that, loose connections do cause heating. And you're right, you should use a calibrated torque wrench. Or damage from external influences like rodents. They could just chew out your wire and again, you've got a series arc. Now, the standard for arc fault detection devices, there is an IS standard. Unfortunately, I don't believe any manufacturer has actually certified them for the IS standard. But if we compare the tripping curve, you can see a B, C, and D curve MCB versus how an arc fault detection device would trip. Obviously, the tripping characteristics is not current. It is just at this level of an arc, this is going to be the tripping time. Now, the observant lot of you might realize that if it's a series arc, there's no current that's going to be produced on its own. So this is actually a sort of a limitation of an AFDD, where if the load doesn't draw more than 2.5 amps, a series arc is not going to be detected by our AFDD. And we'll get to why slightly later. So the product standard goes into, so 2.5 amperes of RMS current would be detected as an arc as 1 second, and so on and so forth. And you can see it's a very different curve to an MCV. The entire mechanism is very different. So how does an AFDD work? This is where things get slightly interesting. Like I said, they're not dependent on current. They're dependent on the signature of an arc, which is the waveform, how long the arc lasts, and how irregular it is. In the sense is how different it is from your normal waveform. So now the interesting thing is there are actually two kinds of arcing. How many of you folks have installed a brushed motor? Brushed motor, anybody? No? But are you familiar with the idea of a brushed motor? Is you have brushes and that go against the commutator. It's not AC. So when you have a brushed motor, the current will jump, and that is called normal arcing. Or how many of you guys have gone to change the temperature, the rotating speed of the fan, and you hear a spark? That's again an arc. How many of you guys have tried balancing the switch? Do not do this. Between the on and off, that's an arc. Some of these are abnormal arcs, some of these are normal arcs. But what will differ is these three factors: the signature of the arc, the duration of the arc, and the irregularity of the arc. But now you might say that this is a developing technology. So, new technology, new products might come out that have different arc signatures. And very interestingly, some manufacturers of AFDDs have introduced AFDDs that can be updated via Bluetooth. This is an entirely different topic, but interestingly enough, this technology is future-proof, unlike our RCDs, where you need a completely new RCD. Now, what about the other protective measures? So this is a very good representation of the different kind of protective measures. Traditionally, we're looking at seeing basic protection, which is your insulation, barriers, placing out of reach, or enclosures. Some of these obviously only applicable for instructed or skilled people. Fault protection, so your either supplementary insulation, mostly it's going to be your overcurrent protection devices. And then, like I mentioned, you have additional protection, which is for your RCDs. Now, a lot of companies are calling AFDDs as the next-gen protective devices. Why? See, overcurrent protective devices can detect short circuits, overloads, and earth faults of negligible impedances, which means that if the current in the earth fault is high enough to trigger the overcurrent protected device, it will trip. But in an arc-like situation, the current jumps. There is no overcurrent happening there, especially in series arcs. And even in parallel arcs, the kind of arcs that AFDDs are built for are not sustained. They keep jumping irregularly. So traditional, and RCDs obviously do electrocution and just earth faults in general. So what can traditional overcurrent protection devices, traditional protective devices not do is they cannot detect high impedance live to live arcing, and they cannot detect intermittent arcing. Now the gentleman asked what kind of AFDDs are available in the market. So here's the standalone AFDD. It's just the unit over here. It usually plugs in as an auxiliary module to an MCB or an RCBO. So that just complies to 62606. Then you have the AFDD plus MCB. So that's 62606 plus 60898 or 60947. That will go downstream of your RCD. Then you've got AFDD plus RCBO, which is the all-in-one solution, which is what's picking up in the international markets now. A single module product, you plug it in onto your VTPN board, and it does earth fault protection, it does overload protection, it does overcurrent protection, and it even picks up arcs. Siemens actually makes this product, and it is available in India. So what does the National Electric Code say? By the way, the clause is mentioned on top there. So it says AFDDs, see if you look at part 1, section 11, AFDDs are required for single phase final circuits lesser than or equal to 63 amperes in electrical installations that basically have people in a vulnerable state. When you're sleeping, you're vulnerable. If you're a child, you're vulnerable. If you're handicapped or disabled, you're vulnerable. So an AFDD is required. What else though? If it's a high-rise building, you look at part 3, section 22, clause 7.3.10.2, it says AFDDs are actually recommended for buildings about 37.5 meters in height. So this is a risk-based approach. See, when you're in a tall building, like Mr. GK said, the time you have to evacuate is reduced. So essentially, you are at a higher risk. So that way, AFDDs will act as sort of a prophylactic to prevent these fires from happening in the first place, because they will disconnect the circuit. Now, when our regulations use the word recommended, what does it mean? It means that it's informative. That doesn't mean that you can do it or you can ignore it. What it means is that the specific protective measure recommended is addressing a concern. The concern being that a high-rise building is a high-risk environment. So you can either choose to go with the recommended protective measure, or you can go with a bunch of other protective measures that give an equivalent degree of protection. How do you decide that? You come with a risk management strategy with your client, with fire authorities, etc. It's out of the scope of an electrical consultant's job. So like I said, the concern is long evacuation times and the risk of persons being stuck, especially by obstructed escape routes. So are there any other considerations when you want to put AFDDs in? See, obviously, if there's a location with a high risk of fire, because let's say it's a wood mill, or they manufacture paper, or you're just simply storing things that are flammable, like a plywood store, you would obviously want to consider an AFDD. If a building is made out of combustible construction materials, say you're in a wooden cabin, again an AFDD is something you would definitely consider. In fact, I would say it shall be installed. If a structure is fire propagating, for example, it's a thatched structure, that the flame will naturally go up that and burn. So again, that has to be considered there. If you have irreplaceable goods, it's in a museum, a bank vault, or something of sentimental value, again, you should consider it. So obviously, this is a very small glimpse into what AFDDs are. You can read the Electrical Installation Wiki. It's a wonderful website. They go into detail on AFDDs. BIMA also has a great guide on AFDDs. ABB as well has produced a very good technical guide going into the tripping curves, kind of arcs, stuff like that. And Eaton as well has a really good guide to AFDDs. So I hope you found this interesting, and yeah, thank you.